2.8 trillion parameters, open weights. Sitting on a public download page right now, for free. That is the largest open weight model anyone has ever shipped, and it landed 3 days ago. 48 hours later, somebody had it writing tokens on a laptop. A 2021 M1 Max, 64 gigs of RAM. The measured speed was 14.6 seconds per token. Not tokens per second, seconds per token. One word is roughly a minute of waiting. A short paragraph is most of an afternoon, and the Hacker News thread went straight to war over whether that is impressive or completely pointless. Here's why the speed is what it is. Kimi K3 is a mixture of experts model. It only touches a sliver of itself per token. Kimi carries 896 experts per layer, 16 fire on any given pass. But 16 experts across 92 layers still means 25.8 GB of rads per token. So 3 things to settle: what actually shipped, what it costs to hold it, and whether any of it is useful. Start with the file. Because the file is the story. 1.56 terabytes of weights publicly downloadable. Kimi K3 is from Moonshot AI in Beijing. 2.8 trillion parameters total. 104 billion active on any given token. 93 layers. A vision encoder on the front, and a context window of 1 million tokens. 69 of those 93 layers run something called Kimi Delta Attention. Instead of a key value cache that grows with every token you feed it, it holds a fixed size recurrent state with per channel forget gates. The other 24 layers are gated latent attention. That mix is why a 1 million token window is even on the table at this size. 3 out of every 4 attention layers stop the cache from exploding. So the memory wall moves off the cache and onto the weights themselves. Hold on to that. It decides everything later. On the front-end code arena, real people voting on which model built the better interface K3 sits at the top, ELO of 1,679. Claude Sonnet 5 is second at 1,631. GPT 4.5 is third at 1,618. It took first place in 6 of the 7 categories they score: brand work, reference-based design, data and analytics, consumer product simulations, and content tools. The one it lost was gaming, where Sonnet 5 still holds the edge. On the harder benchmarks, it is closer to a coin flip. GPQA Diamond, the graduate level science set, 93.5 for K3, 94.1 for GPT 4.5. Terminal Bench 2.1, agents doing real shell work, 88.3 against 88.8. But on BrowseComp, where the model has to find things on the live web, K3 takes it outright, 91.2 to 90.4. The license is not MIT, and that is worth reading before you build a company on it. Moonshot wrote their own document. You can download it, run it, fine-tune it. But commercial inference above $20 million annual revenue triggers a separate arrangement with them. 99,000 downloads in a month, 8,000 likes on the model page. For a file, the overwhelming majority of those people cannot physically store. And for scale, the previous Kimi was around 1 trillion parameters. This is the steepest single-generation jump the open weight chart has seen. So why is a 2.8 trillion parameter model only 1.56 terabytes on disk? In BF16, 2 bytes a parameter, it would be around 5.6 terabytes. The format is MXFP4. 4-bit block floating point, where a group of weights shares 1 scale factor, and each weight keeps 4 bits of its own. Native on Blackwell and MI 355 class silicon, and it is applied selectively. The expert weights, which are the bulk of the model, go to 4 bits. The routers and attention projections stay higher, because those are the parts where a rounding error turns into a wrong answer instead of a slightly worse one. Here is the part that matters most. Moonshot did not quantize this afterwards. They trained it that way. Quantization-aware training running through supervised fine-tuning and reinforcement learning both. So the model learned to live at 4 bits rather than getting squeezed into them at the end, which means the 4-bit file you download is the same precision the paid API serves you. Their co-founders confirmed exactly that in an AMA the day the weights went up. Then Unsloth shipped a quant ladder on top of it, which is the thing that turns a data center artifact into something a very determined person can attempt at home. The smallest build is UDQ1S at 594 GB. 1-bit M is 649, 2-bit XXS is 711, 2-bit XL is 861, 4-bit lands at 1.51 terabytes, and 8-bit at 1.56, same size as the original, and you pay for every step down that ladder. The 1-bit S build agrees with the full model on 78.9% of next token picks. 2-bit XL gets that to 90.4, 4-bit is effectively the original. One correction while we are here. You will see 555 GB quoted for the 1-bit build in a few places. I went looking and could not find it on the published table. The number today is 594. Boring beats wrong, which brings us back to the laptop. The project is called DeltaFin. It went up 2 days ago from a developer publishing as GAA Media, MIT licensed, sitting at 274 stars as I record this. It splits the model in half conceptually. There is a resident spine, the attention layers, the shared experts, the latent projections, the embeddings. About 114 GB quantized down to 60 in INT8, read layer by layer off local storage for every token. And then there is everything else. 80 2,432 routed experts, roughly 1.45 terabytes of them, so DeltaFin does not load them. For each token, the router names 16 experts per layer. It reads exactly those, 1 HTTP range request per expert, 17 megabytes at a time, into a disk cache that grows as you use it. Do that arithmetic and you get the number this whole project lives or dies on. 16 experts, 92 layers, 25.8 GB of reading for one token. Off a local SSD, that is about 4 seconds. Streamed over a network, it is 3 minutes. Now the part that made me stop scrolling. The first working version took 24,429 seconds to produce a first token, 40 minutes, for one token. The current benchmark on the same machine is 28 seconds. Steady decode went the same way. Roughly 20 minutes a token down to 14.6 seconds. That is about 82 times faster. And this is version 1 of a project that is 2 days old. The speedups are unglamorous and specific, which is exactly how you know they are real. A fused kernel that dequantizes MXFP4 and runs the matrix vector multiply in one pass. Neon on Apple Silicon, AVX2 on x86, an int8 spine that halves per token I/O. A packed output head worth 17% on its own, and it stays exact. Greedy decoding, lossless nongram speculation. Same prompt produces the same tokens, run after run. The limitations are stated plainly in the README, which I appreciate. Greedy only. Temperature and top P are ignored entirely. One request at a time. A second concurrent request gets a 429. And long prompts are expensive because prefill has to touch far more experts than decode does. You also need the disk. 1.7 terabytes for a full local install, 5 to 10 hours to pull it down, or 215 GB if you keep the cache small and stream the rest on demand at 3 minutes a token. Somebody in the community ran the same code on an NVIDIA DGX Spark instead. BF16 on CPU took 865 seconds. And 8 on CUDA took 221. So, back to that thread, 136 points, 90 comments. Almost all of it is one argument having itself over and over. A commenter called C-Crealist put the case against it as bluntly as it can be put. No one will ever drive any utility from running models at this speed. Give me the use case. Give me the token counts. And the arithmetic is on his side. 1,000 output tokens at 14.6 seconds each is 4 hours of your machine doing nothing else. The same 1,000 tokens through Moonshot's API cost about 1.5 cents and arrive before you finish reading this sentence. The author's answer is the line I keep turning over. He said the interface matters more than the raw rate, and then added that he can probably only write about 1,000 good tokens in a day himself, which is either a dodge or the most useful sentence in the thread. A third commenter reframed it completely. It's fun. And it answers the question of what happens if you wake up tomorrow and the data centers are gone. Weights on your own disk are the one version of a model that cannot be switched off from somewhere else. The maintainer refuses to oversell it. The README says in plain words that this is a research artifact and not a practical chat setup. He calls it an existence proof and a test bed for streaming inference. That is the correct claim to make. Meanwhile, on the model page, somebody asked the obvious question. Can I run this on my MacBook? The first replies were a stack of maybe 8H200, then 12H200, or 9B200. The third reply pointed straight at DeltaFin and noted the author had made a lot of progress in about 12 hours. If you want to serve it properly, one 8-way B 300 node gives you around 2.3 terabytes of memory, which fits the weights plus the KV cache at 1 million tokens of context on a single machine. Even the smallest 1-bit quant asks for 610 GB of RAM and VRAM combined before it will load. 2-bit XL wants 880. And here's the awkward bit of timing. Back in March, Apple pulled the 512 GB option off the Mac Studio configurator entirely and raised the price of the 256 upgrade by $400. Memory shortage. The consumer ceiling is 256 now. So the one machine a person could reasonably own that almost held this model stopped being orderable in the same year the model shipped. The Frontier became downloadable, and the hardware to run it got harder to buy. Both of those are true at the same time. K3 was not the only drop this week. SK Telecom put AXK2 on Hugging Face. 688 billion parameters, open weights, built in Korea, aimed squarely at manufacturing, defense, and biotech. Across 14 benchmarks, it averages 32 points above the model it replaces. Long context and agent scores moved by roughly 84. They have said the next one is aiming at the trillion mark. Line the shelf up, and it looks nothing like it did in spring. Kimi K3 at 2.8 trillion. DeepSeek V4 Pro at 1.6 trillion. GLM 5.2 at 744 billion with 40 billion active, smaller than K3 and still scoring above it on the Aggregate Intelligence Index. Parameter count stopped being the score a while ago, but the bottleneck did move. Getting hold of frontier weights used to be the hard part. Now it is a download link. The hard part is having somewhere to put 1.5 terabytes and enough read bandwidth to pull 26 GB per token. 14.6 seconds a token is not a product. It is a receipt. It says the model is a file, the file is on your disk, and everything between that and a usable assistant is engineering rather than permission. And engineering is the thing that went 82 times faster in a fortnight. DeltaFin, the Unsloth quants, and the model card are all linked below. If you have got the disk, the README is a good hour. Thanks for watching.